Hello, everybody. Welcome to today's Anti-Siphon Anti-Cast. Thank you so much for joining us. We do this pretty much every single week on Wednesday, and we appreciate you joining us. If you're watching the recording, hello and welcome from the past. If you would call it pre-show banter, you know that the past either exists or it doesn't. None of this stuff makes any sense. One of the things that we talked about during pre-show banter is that how I do not know how computers work. Like, I know it does work, and I know that things happen. I know that you can see me right now. I know that all this was interpreted by computers. And so the fact that we uploaded and downloaded and made things happen, there's cameras, there's all this stuff. I really don't know how it all works based on electrons and ones and zeros and all that stuff. So I'm here to learn from Doc how this is not magic, how this does work somehow, and how we can learn to use this as foundational knowledge for cybersecurity. And then from here, we can keep building on that. So if you are in the same boat as me today, hello and welcome. Thank you so much for being here. If this is not new to you, then cool. Let's validate some of your own thoughts and feelings about it all. But Doc is a fantastic educator. I've known Doc for years. Doc has a passion for teaching, and so you're going to get a chance to learn from someone who really, really wants you to know this, and he wants to be the one that gets a chance to share it with you. So thank you so much for being here. I'll be back for Q&A. Doc, it's all yours.
Awesome. Thank you so much, Jason. I appreciate the kind words. And folks, don't worry about Jason and his quandary about how computers work. We're getting him the help he needs. Okay. So welcome everybody to an introduction to numbering systems. And before we even get started with playing around with numbers, I want to reassure everyone here is that there's no prerequisite knowledge that you have to come in with in order to understand what we're going to talk about here. We're going to start right from the basics. We're going to ramp up pretty quickly. It's a lot of material, a lot of things you're going to learn in this 1 hour, but I don't want any of you to feel left behind. My slide deck is, at first I was thinking I'm a little light on the slides. No, I need more slides. I need more slides. And then I realized, you know what? I want to make sure that I can give you guys the time to really grok the material, to understand what's going on. And so I was like, no, not more content, less content. Let's focus on those foundational concepts. And so let's go ahead and get started right from the beginning here and talk about why this is important. And why it's important is because in order for people to talk to one another, they need to have a shared common language. Computers are the same way. In order for computers to talk to one another, they need to have a shared common language as well. For those of you who have attended some other presentations of mine, you will recognize that this is Alice and Bob. Of course, when you talk about cryptography, you have to talk about Alice and Bob. And so I started creating these characters and decided, you know what? I'm going to keep them going forward to all of the other classes and just kind of do a branding thing with them. So we've got Alice and she wants to talk to Bob. And so she is going to say, hi, Bob, I'm Alice. I have a request for you. Now, she's saying this in English. Now, if Bob can hear and if Bob understands English, he can understand what Alice says. All right. But he needs to understand the language that Alice is speaking. Bob hears Alice. He understands the message has meaning. And now he can he'll respond with English back. Why not? So he says, hi, Alice, what can I help you with? The reason these two could have their conversation is because they both understood a common language. Now, let's say we've got a disconnect. Let's say Alice started speaking Spanish and Bob doesn't understand Spanish. Bob can still hear Alice, but the words have no meaning to him. Now, let's say Bob tries to respond by saying, I'm sorry, I don't understand what you're saying. Now let's, for a second, assume that Alice doesn't speak English. She doesn't understand English. She only understands Spanish. And so she can hear Bob, but she's lost the meaning. She's like, okay, she doesn't understand. And Bob's like, huh? There's no connection here because the two of them are speaking entirely different languages. Computers have their language. Computers understand ones and zeros. And so at the most basic level, that's how a computer understands the meaning of information. It's how it transmits that information to others. It's how it receives information from others. And in order for the computer to have meaning to those ones and zeros, the computer needs to understand how those ones and zeros relate to information, just like with Alice and Bob in their conversation. There are many different areas of cybersecurity where it's of utmost importance for us to understand how the computer communicates with its ones and zeros. Cryptography is something I already mentioned. Networking I've already mentioned as well. Basically, Alice and Bob communicating, they are a network at that point, right? They're two parties communicating with one another over this shared medium. Forensics, and there's so many different areas where if you understand the language that the computers speak, you will be able to understand how the computers communicate. And so that's where we're going to start from. And of course, as I mentioned in pre-show, and I've got it on the slide here, we do have an introductory to networking course coming sometime in early 2026. All right, so let's talk numbers. Let's talk ones and zeros. First, when Alice was speaking to Bob, she was speaking English. And then on the second slide, Alice was speaking Spanish. Computers speak a language of ones and zeros, and we call that language binary. Binary is that one and zero construct of is it on, is it off, is it plus, is it minus? And so think of it like a light switch. Imagine if the light switch is on, we record the state of the light switch as a 1. Okay, that's the value of 1 when that light switch is on. But then if we were to turn that light switch off, it's the same light switch. It's just now it's in a different state. That different state, let's go ahead and call that a 0. And the way that networking works is when you're sending communications over an Ethernet connection, whether it's your wired connection at home or Wi-Fi or whatever it is. Basically, the way that Ethernet works is it sets up a clock between the two devices. There's this drum beat between the two of them, beat, 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 beat in time. And then if there is a pulse of electricity present at a certain point in time, at a certain beat, the computer knows that as, oh, that's a 1. And then on another beat, let's say at that point in time, there's no electricity flowing. Okay, that's a 0. And so basically a computer can send, the pulse, no post, pulse, 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 no post, post, no post. And so back and forth, 1, 0, 1, 1, 0, 1, 1, 0, 0, 1, 1. And so that's how computers share information from one to the other. All right. So now, if we have a single 1 or a single 0, that's known as a bit. And there's only 2 possible values we can represent with a bit of information. Is it a 1? Is it a 0? All right, that doesn't give us a whole lot of options there. So what do? Is we're going to take a bunch of those bits and put them in a row. We'll call that a string. This string of ones and zeros, let's say there's 8 of them. 8 bits in a string together are called a byte. Now, while we only had 2 possible combinations with a bit, with a byte, even though there's only 8 of them, we jump from 2 possible combinations to 256 possible values, 0 through 255. As we were talking about in pre-show, somebody had mentioned that they were teaching their kids how to count starting with 0, and that's just insane. I'm sorry. That's why we can't have nice things in this world, folks. We're teaching the kids to count starting with 0. We don't start counting with 0, right? We start counting with 1. So computers are different. Computers start counting everything with 0. And so the lowest value of a byte would be 0. The highest value of those 256 is 255 because we started counting at 0. There's 256 values there, 0 through 255. Now, sometimes we need more than a bit, and maybe we need less than a byte. I am not going to take a byte of information to describe something that I can describe in a bit. I'm going to use the lowest possible number of bits to conserve my energy. There's no need for me to be redundant. And let's say with a byte, I set all those eights, the ones and zeros to ones. And that means that that's yes. One is yes. One. That's yes. That's too much. That's too redundant. And so I'm going to just use a bit, just one. All right. And no, instead of being 0, 0, 0, 0, 0, 0 for no, just 0, right? So sometimes I need more than a bit. Sometimes I need less than a byte. What if I were to take that byte and like Fruit Ninja, just go shoof, cut it right down the middle? Now I have 4 bits. We call that a nibble. And you think my jokes are bad? That's real. Half of a bite is a nibble. It's fun size. It's not the whole candy bar at Halloween. It's a half of a candy bar, right? Because your neighbors are being cheap. So with a nibble, it's 4 ones and zeros. That gives us 16 possible combinations, 0 through 15. Now, computers, when they speak binary, they're talking in bits and bytes and nibbles. And that's different than how humans count. Because with us humans, we have what's called a base 10 numbering system. When cave people started speaking to each other and trying to communicate information, they're trying to indicate numbers. We've got 10 fingers on our hands. And so why not? Let's count with that. So the first cave dwellers are like, I find it interesting. I find it fascinating that as the different societies of the world grew up, all of these different societies created different languages. That's why we have English and Spanish and all of a sudden I'm blanking on every other one, Mandarin and Farsi, whatever language it is, all hundreds of different languages across the world. Yet almost all of those civilizations had created a base 10 numbering system. And it's probably because of the 10 fingers and 10 toes. Now, there was a tribe in South America that when people first made contact with them, it was like over 100 years ago now, those people had a different numbering system. Their numbering system was 1, 2, 3, many. I guess after 3, there's no point counting. You got a lot of them. Why does that matter to you? How many there are? You have a bunch, right? But for the rest of the world, it's a base 10 numbering system. What we're going to do today is we are going to try to make sense of that binary numbering system to our world of base 10. All right. So let's go ahead and explore what that would look like here. I am going to, you can ignore what's on the screen right now. I'm just going to use the white space in this screen to show you how we convert the number 231 into the value 231. I'm going to draw it, then I'm going to erase that drawing, and then we're going to, there's a reason why we're doing it that way, is that I'll go ahead and use this 231 right here. Now, decimal is a base 10 numbering system. We've got 10 possibilities, 0 through 9. So let's start with this base of 10. And what we're going to do for the position all the way to the right, that's our lowest possible value. That is the value, the base of 10 to the power of 0. Oh, math like that. This is the worst. This is as bad as it gets, folks. All right. And it's easy. It really is. All you're doing with powers of a number is you are multiplying that number to itself a certain number of times. And that's the power. All right. 10 to the power of 0 is what? Does anybody know what 10 to the power of 0? So we already have an answer here before I even ask the question. It is 1, right? So that is the ones position. It's 10 to the power of 0, makes it the ones position. Now let's move to the next value to its left. We have that base of 10, but now we're going to raise it to the power of 1. We're going to increment that power each time. And I bet you guys know where I'm going with this. Now, what is 10 to the power of 1? What's any number to the power of 1 is the original number, right? So this would be 10. This is the tens position. Everybody good so far? I definitely encourage everybody to share in Discord. While Discord isn't up on the screen here, I can see it on this iPad, and I just want to make sure that everybody's following along. If I lose you at all, I am happy to go back and make sure that we got it. Everybody good so far? And somebody put 11. I hope you're messing with me. Let's see here. So some other people are putting different numbers here. So now let's go ahead and go one more to the left here. This 2 to the left is 10 to the power of 2. What's 10 to the power of 2? Well, remember, those powers are just simply the number of times we're multiplying that number to itself. And so 10 to the power of 2, 10 times 10 is 100. Yeah, it's not 200. Some folks are messing with me here. 2 times 10 to the power of 2 is 200. Yeah, that's one way of putting it. Let's go ahead and do 100. Yeah, 10 to the power of 2 is 100. What I'm going to do now is I'm going to take this 2, 3, 1, and I'm going to bring it down here. And I'm just simply going to do some math. Starting on the right, we have 1, and we're going to multiply that to the number 1. What's 1 times 1? Of course, it's 1, right? And don't start with the 6, 7 jokes, folks. I'm too old for that stuff. It makes my head explode, and I need a nap afterward. And in the future, when somebody's like, what's the problem with 6, 7? This gets old really fast, right? Oh boy, no, I tempted it. All right, so 1 times 1 is 1. Let's go ahead and go to the 3 next to that. 10, which was the value of this place, times 3 is 30, right? So 10 times 3 is 30. So far, so good. Let's move 1 to the left. We've got 2 times 100. 2 times 100 is 200. If we add those together, 200 plus 30 plus 1 equals 231. Congratulations, Doc. You just converted decimal 231 into decimal 231. What was the point of that? All right, let me go ahead and erase this and show you why we were doing this. Erase, 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 just like a blackboard. Got to get it all. Ba-ba. Now I'm going to show you the same thing on the slide. Just wanted to talk through that a little bit before I actually showed you the items on the slide. So we've got this number 231, and you can see, oops, I got to close out of this thing there so the slide advances. Here you can see the place values, 10 to the power of 0, 10 to the power of 1, 10 to the power of 2, that we've got the ones position, we've got the tens position, we've got the 100s position. We are now going to, this is the fun part. I put some animation in the slides. We're going to have that 231 go beep, down to the bottom there. And then what's 1 times 1 is 1. 3 times 10 is 30. 2 times 100 is 200. We add those together and we get 231. Have I lost anybody so far? How's everybody doing in Discord land there? Everybody get what happened here? Questions, comments, concerns, hopes, dreams? Yep, but those who, oops, and now it's already scrolling on me there. Yep, but those who don't do it really don't know why they are doing it. Yes. So what we're going to do, we are going to get to the why here in just a little bit by relating it to a different numbering system. Now, let's change everything. Everything's changed. So we've got binary. Those computers understand only ones and zeros. Now I've got a byte of information here, 11100111. And their positions are not arbitrary. They're in a very distinct pattern, just like decimal, because now we have a base of 2. And then we raise that base to the power of 0 and 1 and 2 and 3 and 4 and 5 and 6 and 7 as we go from right to left. Wait a minute, it's a byte. Why did we end on 7? Because we started with 0 at the beginning. All right. So what is 2 to the power of 0? Just like 10 to the power of 0, any number raised to the power of 0 is 1, right? And so that is the ones position in binary. Now, we move one neighbor to the left. 2, which is the base of the numbering system, raised to the power of 1 is the 2's position. All right, so far so good. And then let's move 1 to the left. 2 to the power of 2 is, whoops, I was hoping that my slide would just advance. There we go. Is 4. All right, 2 times 2 is 4. And move 1 to the left. 2 to the power of 3 is, don't say 6. It's not 2 times 3. It's 2 to the power of 3. 2 times 2 times 2 is 8. Does anybody notice what's happening to these values as we move from right to left? What's the pattern here? They're doubling each time. Yeah. And so when we get 2 to the power of 7, it's 128. That's the 128 position. Now I'm going to do the same thing that we did for decimal here with binary. I'm going to bring that byte 11100111 down to the bottom. And now we're going to do the same thing we did in decimal here with binary. 1 times 1 is 1. 2 times 1 is 2. 4 times 1 is 4. 8 times 0 is 0. 16 times 0 is 0. 32 times 1. I think you guys got the idea here, right? 64, 128. Now, let's add those numbers together. 128 plus 64 plus 32 plus 0 plus 0 plus 4 plus 2 plus 1 equals our magic number of 231. Wow. So, what have we just learned here is us humans see 231 as 231. A computer doesn't see that number that way. The computer sees it as a byte, 11100111. So that byte is the same value as decimal 231. Awesome. All right. How's everybody feeling? Feeling good? All right. Everybody get what we did there? Okay, so Eric says not really. Subnets must be now. This is not a networking class. Dude, let's keep it real at this level here. Don't even get me started on subnets. We will do some subnetting in the networking class for sure. So, alrighty, now let's go ahead and do some practice here. You guys ready? Alice and Bob are ready. They've done their stretches. They're ready to go. Let's practice this together. Here I've got those 8 values, 1, 2, 4, 8, 16, 32, 64, and 128. And we have a byte, 0101 1011. We're going to do the same thing that we did earlier here, just in a more compact version. 128 times 0 is, and I'm working from left to right here. It doesn't matter which order I do them in. I just did them in opposite lands, starting with the highest value here. First, 128 times 0 is 0. 64 times 1 is 64. 32 times 0 is 0. 16 times 1, you guys get the idea here. 8, 0, 2, 1. And then all we have to do is add those values up. 64 plus 16 plus 8 plus 2 plus 1 is 91. Awesome. So the byte 01011011 is the value 91 in decimal. Let's go ahead and do another one here. Here, we've got the byte 10001100. We're going to do the same thing. There's a 1 in the 128 spot, so that counts. There's a 0 in the 64, so that's a 0. 32, that's a 0. 16, that's a 0. There's a 1 in the 8 spot, so we count the 8. We count the 4. We don't count the 2. We don't count the 1. 128 plus 8 plus 4 equals 140. Awesome. Everybody following so far? Following good, hopefully? Oh, now everybody's stuck on subnets. Oh, you guys. Oh, boy. All right, so let's go ahead and do one more for practice. Here we've got the byte 00000000. So if we've got a 0 in the 128 spot, it's a 0, 0 in the 64. You guys get the idea here, right? It's going to be all zeros. And so what is that value? Is the value 0? Okay, that makes sense. That's why computers start counting at 0, because whether it's a bit or a byte or a nibble, that first value is always 0. Now, there are a few sanity checks that we can do along the way to make sure that we have things right. How do I know this number is correct? Well, we're going to reverse engineer it in just a little bit. But what I'm going to do here is just a quick sanity check. There's a few things I can check to make sure that this actually makes sense. This 91, does that make sense for 01011011? Well, you notice anything about this first value in comparison to all of the other values? What are all the other values? What do they have in common? What do you think, folks? They're all even numbers, right? And so those always make even numbers. Now, this one being a 1 itself, if that bit is set to a 1, what do you think we can assume about the decimal number? If that 1 is set to a 1, it must be an odd number or the number 1, right? Is this number odd? It turns out it is. Yes. Okay. Sanity check complete. Let's go ahead and check this one here. We can see that the first value, that bit is a 0. So what does that say to us? Is that whatever this decimal number should be, it's either going to be an even number or 0, right? Now, here we check. That's 140. It is an even number. And so bing, 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 we now have a sanity check there as well. Now let's go ahead and we're going to do another set. And of course, it's set to 0 here, 0. Yes. Okay. Perfectly fine. Here's another sanity check. The value all the way to the left is 128. And that is the highest value of all of these, which means that if that bit is set to a 1, what must we know about the decimal value of the number? What do you think would be the case here? If that 128 position, the bit is set to 1, what would it be? Would have to be equal or greater than 128. Exactly. Exactly. And if that bit is set to a 0, then the number must be lower than 128. All right, let's go ahead and check our sanity here again. We can see that this is set to a 0, which means this value should be below 128, and it is below 128. Yay, we did it. Now with this next one, we can see that there's a 1 in the 128 position. Well, that must be 128 or higher, and it turns out it is higher than 128. Yay! And then Here, of course, with 0, it's going to be below 128 because 0 is 0, and we're all good there. Woohoo! How's everybody feeling so far? And as it's said in the chat here, at 255, that's the highest value we could represent. Yeah, if these were all set to ones, it would be 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1. That's 255, creating 0 through 255. What's really cool about binary numbering is that there is always a way and only one way to represent every decimal number. Isn't that neat? When I learned this, I don't know about you guys, but when I learned this, I said that math is cool. Math is really something special here. All right, so let me erase all of that because it'll actually follow me to the next slide if I don't. There we go. We cleaned up the eraser. All right, so let's go ahead and continue on. Got to close out of the pen option there. All right, Alice is like, yay, we did it. Woohoo. Let's go ahead and do the reverse. Now we've got a number 80, and we need to determine what byte, what combination of ones and zeros would create the number 80. So now we're doing it in reverse. There's a really easy way of doing this. The way that we used to describe it, and it's funny because it feels like it's falling out of fashion now because we're turning into such a cashless society. People don't know how to give out change anymore, and it's just weird because what we're going to do here is we are going to use these binary values to give out change for 80. Let's say you have a customer that it gets $80 back. And in your cash register drawer, you've got these binary values. You've got $128 bills, $64 bills, $32 bills, 16, 8, 4, 2, and $1 bills. I ask you, if you're giving the customer 80 in change, would you give them a $128 bill? I hope not. That's too much, right? And so that would be a 0. Now, would you give them a 64 if you're giving them 80 and change? Yes, you would. So that is a 1. Now, we've got some math to do here. We just gave them a $64 bill. We were giving them 80 and change. How much change do I have to give them yet? So now I am going to take the number 80 and I am going to subtract 64 and I get 16. I still need to give them 16. All right. So if I need to give them 16, would I give them a 32? No. So that would be a 0. Would I give them a 16? Yes, I would give them a 16. And in fact, 16 is exactly the remainder that I still need to give them. 16 minus 16 is 0. And so what do we know about all of the other positions, 8, 4, 2, and 1 here? They would all be 0, right? Isn't that neat? We have just converted a decimal number now into a byte. The decimal value 80 is the same as the binary value 01010000. Everybody following so far? Shall we do another one for practice there? Let's do another one for practice. Here we go. All right. Now we've got the value 173. Would you give them a $128 bill if you're giving them 173 and change? 173 is bigger than 128, so absolutely we would do that. So that's a 1. Now, that fact 128 from that 173 to see what our remainder is. So 173 minus 128 is 45. If we're giving them 45 and change, would we give them a 64? No, 64 is bigger than 45, so we wouldn't. That's a 0. All right. Would you give them a 32? 45 is larger than 32, so yeah, we would give them a 32. So that's a 1, right? So far, so good. Now, I need to subtract that 32 from the 45. So here we've got 45 minus 32 equals 13. All right, so would I give them a 16? I wouldn't give them a 16. That'd be a 0. Would I give them an 8? Yes, 13 is higher than 8, so I would give them an 8. Now, 13 minus 8 is 5. Would I give them a 4 if I still owe them 5? Yes, I would give them a 4. 5 is bigger than 4, so that's a 1. And so now I subtract 5, the 4 from 5 to get 1. Would I give them a 2? Nope, so that's a 0. Would I give them a 1? Yep. And then 1 minus 1 is 0. I gave out all the change successfully. Woohoo! Wow. So what we just did is now we've converted 173 into the byte 10101101. Awesome. Woohoo. There are no 2s in binary. Oh boy. Let's do one more here, folks. Here we've got the number 255. And I think you all know where this is going, right? In my head, I know 255, just committed that to my long-term memory that would be 11111. But why would it? Because 255 minus 128 equals 127. This is a really weird mathematical, but I just think is kind of a loop here. You'll see that for this entire byte, every time we subtract the value from our remainder, it's going to be 1 less than what we just subtracted. 128, 1 less is 127. I'd give them a 64. 127 minus 64 is 63. Isn't that weird? I would subtract 32. 63 minus 32 is 31. You guys can see a countdown happening here, right? 16. Yes, we give them a 16. 31 minus 16 is 15. I love when math aligns like that, where it's just like, this is so cool and bouncy. It's just like, wow, the numbers are just all making sense to us here. And so 8 subtracted from 15 would be 7. And as you guys know, 7 minus 4 would be 3. 3 minus 2 is 1. And we've given out all of the change. We already knew, because we committed to memory, that 255 in decimal would be the byte 11111111. But now we see the math that shows that it would be that, right? Everybody good so far? And the comment, last digit is going to be a 0. I hope so. Yeah, if it's not a 0, we did something wrong here, right? We really messed up. All right, so far so good. Let's do the opposite. Let's do what we just did earlier and add the numbers together. Here we had the byte 0101. 0000. You see that 64 plus 16 is 80. That was the number that we converted into a byte. So now we're not just doing a sanity check here. We are absolutely working our way backward to make sure that it was correct. Kind of like I learned not too long ago, for some reason, I don't even know why, but I had it was something having to do with the Mason-Dixon line and how the cartographers were charting out where the Mason-Dixon line is in the US. And I found that it was really fascinating. What they would do is that they would measure angles based on the amount of distance. So they measure distance, they measure angle, they measure 2 points to create a triangle. And therefore, they can tell things like, if they know the elevation, they can tell how far something is away. If they know how far something is away, they can tell the elevation. And so as you're going through these hills and valleys, making sure that you're drawing a straight line right through the terrain. Well, what those cartographers would then do is, once they made a measurement from the spot they were at, they would go to the location that they just made the measurement of, and they would measure back to the original spot, because those numbers should match. If they don't match, they know they got something wrong in their calculations. We're doing the same thing here. We're just simply confirming that 0000, I'm sorry, is the value 80. And that's what we started with when we created the byte. And we can see with the second one, 128 plus 32 plus 8 plus 4 plus 1 is 173. And then 1111111. You add all those numbers together, you get 255. We can also do our other sanity checks if we want. We really don't need to at this point because we just literally checked our math to make sure that's exactly what it needed to be. And Bob is stoked about that. All right, so now we're going to make things weird. Now we're moving into nibbles. Oh boy. So nibbles have a very special place for us when it comes to numbering systems. It's exactly half of a byte, but which means that 2 nibbles are a byte. But nibbles actually gives us the opportunity to create an entirely different numbering system. Ooh, intrigued? You should be. I hope you're intrigued because that's what we're going to talk about now. Imagine I've got this nibble of 1011. We're going to start with that same pattern we did before of the value all the way to the right is the ones position, then 2s, 4, 8, same as before. So let's go ahead and do the math. 8 times 1 is 8, 4 times 0 is 0, 2 times 1 is 2, 1 times 1 is 1. This nibble of 1011 is the value of 11. All right, so far so good. Let's say we have a nibble of 0000. You guys all know we've already figured this out. That would be the decimal value, of course, of 0. And then what if that nibble is 1111? What do you think, folks? What would we have there? Just simply 8 plus 4 plus 2 plus 1. It would be 15, right? All right, so our nibbles give us 16 possible values, 0 through 15. Now, wait a minute, we got a problem here because a nibble is what we refer to as a base 16 numbering system because there's 16 possible values. But when we have decimal numbers, there's only 10 possible combinations, 0 through 9. I could represent any decimal number as hexadecimal as long as it's below 10. But once we get to 10, how do I stick a 1 and a 0 into one space there and say, oh, this is a 10, squish it together? That isn't going to work for us. And so what we actually do with what's called hexadecimal, base 16 numbering systems, where you've got 4 bits, is 0 through 9, no problem. We have decimal numbers for that. 10, instead of trying to fit a 1 and a 0 in one space that isn't going to fit because it needs to be one character, we're going to call 10s A's. We're going to call 11s B's. 12s will be C. 15 will be F. So now with hexadecimal, where we have 16 different values, 0 through 15, 0 in decimal is 0 in hex. And the highest value, 15 in decimal, is F in hex. I know we just had to make things a little weird here for a moment because what we're going to do now is we are going to take those same values we had earlier, those nibbles of 1011, that was our top example. Remember when we added 8 plus 2 plus 1, we got the value 11. Well, I can't put hexadecimal 11 there. That's not a thing. So 11, we can see is the hexadecimal character B. Now, one of the things you might wonder, does it matter whether they're uppercase or lowercase letters? Doesn't matter. Computers don't care. Case doesn't matter here. An uppercase B, lowercase b means the same as far as hexadecimal values go. Some operating systems will display it as an uppercase letter. Some will display it as a lowercase letter, and it doesn't matter to me. I don't care which one. Here we can see that in our second example, 0, of course, would be 0. Hexadecimal 0 and decimal 0 are the same. And then for 1111, 8 plus 4 plus 2 plus 1 was 15 in decimal, and 15 is F. All right. And folks, you don't know how much I like BoJack Horseman. I love that meme there. I could practically tell you what episode that was. I've watched that show so many times. Thank you for posting that meme. I appreciate that. So now we've talked about bits. We've got two possible combinations. We've talked about bytes where we've got 256 possible combinations. We've talked about nibbles where we have 16 possible combinations. Where is all of this going? Well, what if I were to take that byte and just chop it in half like Fruit Ninja and now assess those nibbles separately? Why would I do that? There's a very distinct reason why. Here I have a byte 01011011. As a byte, it's the value 100. I'm sorry, 191. 91. Wow, there's not too many numbers in my head there. Now, let's chop it in half and assess those separately. Here I'm going to take that 0101 and I'm going to slide it on over into a nibble chart. Yes, those first 4 bits in the byte had values 128, 64, 32, 16. That doesn't matter anymore because we have just made this a nibble. We've nibbleized it. And I just came up with that word on my own there. Patent pending, patent pending. We nibbleized that portion of the byte. And we're going to assess it separately from the other nibble. And so there's a 0 in the 8 spot. There's a 1 in the 4 spot, a 0 in the 2, 1 in the 1. 4 plus 1 equals 5, which would be hexadecimal 5 for us, right? Okay, so far so good. Now let's take that other nibble, the lower order nibble. We're going to call it here. And we are going to run that through the nibble chart as well. We're going to nibbleize it. So 1011. We assess it. We've got 1 in the 8 spot, 0 in the 4, 1 in the 2, 1 in the 1. 8 plus 2 plus 1 equals 11. I can't put 11 there. Does anybody remember what character in hexadecimal represents 11? B, exactly. Very good, folks. And so that would be B. Now, here's the really cool part. Instead of having to write out the byte 0101111, I can just simply say hexadecimal 5B. I was like, wow, in just 2 characters, I've represented those 8 bits. The importance of hexadecimal characters is, and it doesn't feel like it at first, it really feels like hexadecimal is created to screw with our heads. Well, it turns out hexadecimal is created just basically so that we can more easily recognize the bytes. Now, let's take that hexadecimal 5B here. And what I'm going to do is let's do the conversion back to in the opposite order. I want to take 5B and create a byte from it. So I separate those two. I've got their separate nibble charts. We've got 5, we're giving out change. So I wouldn't give them an 8. I'd give them a 4. I wouldn't give them a 2. I'd give them a 1. 4 plus 1 is 5. Yep, we've got that. That's our value there. And then with the B is 11. I give out change. I'd give them an 8. I would give them a 2. I would give them a 1. And so far, so good. And so now we've just shown that 5B actually converts into the byte. We've got 0101. Whoops. Should be coming down here. That's one of the slides I had. This stuff is so fresh, folks. I haven't even finished the materials yet. So let's go ahead and take this here. We'll go 0101. That's what I got from here. And then from here, 1011. I can then take that 64, 16, 8, 2, and 1. That's where the ones are. And then add those together. What's 64 plus 16 plus 8 plus 2 plus 1, folks? It's our original number, right? What was our original number? Wait a minute. Is our original number? Let's go back here for a second. It was 91. And when we added them together, we got 91. Did that really work? Yes, it is 91. Yay. Wow. We're just killing it here, everybody, aren't we? Ooh, it's time to party. Is everybody having fun? Is this a good time? Wow, too much, so much fun, it shouldn't be legal, right? So, binary is a base 2 numbering system. We have two different values, 0 and 1. Decimal is a base 10 numbering system. We've got 10 different values, 0 through 9. Hexadecimal is a base 16, 0 through 15. And so then, wouldn't a byte be a base 256 numbering system? Mind blown. Huh. I didn't see that one coming. Bytes are a base 256 numbering system. Do you know why that's important? It's because guess what? There are numbers bigger than 255 in this world, right? Oh, that's right. There are numbers bigger than that. So, how do we create bigger numbers? We are going to just put more bytes together. Now, I don't like how busy this screen is with all of this math on it. But what I want you to recognize here is that the lower byte here is now that, let me write the margins here. This byte here is 256. The base of the numbering system, remember a byte is base 256 to the power of 0, which is the ones position, right? So this would be the value of that byte times 1. If we move one position to the left, guess what? 256 to the power of 1 this is the 256th position. So it would be the value of the byte, 206 times 256. Oh, so now I just simply add up 52,736 to this 107 to get a value 52,843. Wow, I can represent bigger numbers. And not only are they bigger, they're exponentially bigger. Guess what would happen if I had 3 bytes together? Yeah, the third byte to the left would be 256 to the power of 2 times the value of that byte. The one to the left of that in a 4-byte value would be 256 to the power of 3. Those numbers keep getting bigger and bigger. If we had a 4-byte number up here on the screen, we could represent values up to 4.2 billion, slightly over 4.2 billion with a 4-byte number. Another way of looking at it is, let's look at our original chart of a byte where we had already determined that every value to the left is twice the value of its neighbor. Well, that would just continue on with the second byte, those bits as well. What's twice 128? 256. All right, that makes sense. That's our base 256 numbering system. In the 512, 1024, 2048, 4096, I bet that when we talk about things like RAM and networking and other concepts like that, some folks are saying, wait a minute, now these numbers are making sense as to why we use numbers like 256, 512, things like that, and why they double each time. Every time you add a bit to that string of bits, you double the possible combinations of numbers. That's some really cool stuff there. I'm going to need a nap after this. Wow. All right, so let me go ahead and erase that. So as the numbers get bigger, we can represent, as the number of bits get bigger, we can represent larger numbers. And now this one will blow your mind. we've got a 16 byte number. 16 bytes gives us 340 undecillion possible combinations. And that's the size of an IPv6 address, right? 128 bits, 16 bytes, 340 undecillion. And in case you hadn't heard the analogy before, how large of a number is that? If you were to take every human on the planet, every human being, and break them down to not their cellular level, not their molecular level, but to the atomic level, you could assign every atom of every human on the planet. There's about 8 billion of us. We could assign a unique 16 byte number to every atom of every human on the planet and still not run out of unique numbers to assign them. That's how big that 340 undecillion is. That's pretty wild, right? But what does this have to do with, things like the English language? And so what we're going to do is we're going to wrap up this hour talking about ASCII, the American Standard Code for Information Interchange, and things get really simple here. I'm going to put a chart into Slack for you folks. I'm sorry, not Slack, Discord. What application are we using here? Discord. There we go. Upload this in there so you guys have a copy of that. There's plenty of places where you can find that. There we go. Took a second. And what I'll do is let me go ahead and share that. And Jason's going to have a fit because he's going to be like, "You're not going to share anything else on your screen, are you?" I was like, "No." And then, now I am, Jason. So here we go. I am now flying without a net, folks. Where do we share this other window? Let's share I'll just share this entire screen.
Mm-hmm.
Yeah, I'm sorry, Jason. So here we've got this chart up here where if I wanted to print a character on the screen, let's say it is the capital A, and now we're not talking about hexadecimal A, and so case does matter here. That byte for capital A printed on the screen is actually binary 01000001. And we can see that if we were converting that binary into decimal, the decimal value would be 65. If we were to convert that byte into hexadecimal, it would be the value 41. Now, be careful. This is not hexadecimal 41. That doesn't exist. It's hexadecimal 41. If you say 41, all of a sudden you've created something that doesn't exist in this real world because it is hexadecimal 4. And do you know what? We could do that conversion really quickly here because I'm feeling it. I'm just feeling the groove here. This hex character 4 represents this nibble, right? 0100, 0100, I said that right. Yep, is a 4. There's a 0 in the 8's position, a 1 in the 4's position, a 0 in the 2's position, a 0 in the 1. So 0100 is hexadecimal 4. And then for this hexadecimal 1, that represents these bits. And so it's 0001. There's a 0 in the 8, 0 in the 4, 0 in the 2, 0 in the 1. And that gives us a value of 1. So that's how we got that 4-1 there. Computers have software on them. Software is instructions that was written by human beings for us to understand what computers are representing with those ones and zeros. So the context and the positions of these ones and zeros is where it's all at. I want to thank everybody for joining us here. I'm going to put my share back on my other screen. Here, where we go. Share it back over here. because I had to promote the class one more time sometime in early 2006. Keep an eye on the anti-siphon training website. We will have a networking class where you will get this plus 7 more hours of amazing content. At least I think it's amazing. I'm the one that created it. So maybe I'm a little biased because, I don't make ugly babies. All of my babies are beautiful. So it's going to be a beautiful course, right? And it is now at the top of the hour. And one of the things I pride myself on as an instructor is to finish on time. So here we are, folks, handing it back over to Jason. And Jason's on mute. Jason's supposed to be a pro. He's supposed to be the pro here.
Oh, wow. I said a lot of nice things about you too. So Doc, thank you for making math and numbers interesting. I'm sure there was a few people here that was like, if my class was like this in college, I would have learned so much more. So thank you for sharing your knowledge in this way.
You know what? You're welcome, Jason. What happened during COVID is my here I was teaching all remotely at that point, right?
Mhm.
Because it's COVID times. And so I was teaching in an office next to my son's room. He was in high school at the time. And he always thought he could hear me through the wall and all of that. And he always thought that I was silly and all of that with just being weird and obnoxious and everything. And so he goes to college a few years later. And the first week of college, he says, Dad, I now understand why you were teaching the way that you did. And he said, this is the biggest compliment any of my children have ever said to me. He said, Dad, I wish that you were my professor in college. I was like,
No.
thank you.
Oh, I love that, Doc. So for everyone that joined us here today, thank you so much. We do this every single week. Real quick, if you are reading our comic book series, The Future Is, issue 8 is in comic book stores today. It's in 600 comic book stores. And then the first volume, issues 1 through 7, will be in comic shops at the end of the year. So if you've been reading that or you want to get caught up, thank you so much. You can at your local comic book store. All right, Doc, I would love for you to just sum up everything in one final thought today for the people sticking around. If you could take everything that you said today in just one final thought, what would it be?
It's that computers speak a language and that we need to understand what that language is to understand computers. I have been in situations as a manager once. I was in a situation where I was being CC'd on all of this networking stuff because I was responsible for the PCI requirements of this payment card system that was on the network. I was getting CC'd on it, but I didn't have to deal with those emails. But I had noticed that the technician between my employer and the vendor, that conversation, they're like, it's not working, it's not working, it's not working. I decide, I'm going to go ahead and dig into the email just a little bit here. I'm pulling this into a conversation where somebody mentioned subnets earlier. One look at that email, and I knew exactly what the problem was because I understood binary. I understood that the network settings that they were putting into the machine were impossible. They wouldn't ever work and solve that problem. I'm sure the technicians were probably embarrassed by the fact that a manager, what does a manager know, had solved the technical problem that they couldn't figure out. Folks, understand how computers work, and it makes your life so much easier with them.
Awesome. Thank you, Doc. I would love for you to join us, all of you, to join us at Wild West Hackin' Fest in Denver in February. If you haven't thought about it or you haven't decided yet, now's the time. And I know you're like, wait, that's in February, like next year, 2026. Yeah, we'd love to see you in 2026 in Denver at Wild West Hackin' Fest. We do this all the time. There's currently, if you take a look in the chat for Zoom, there's a link to participate in a free CTF based on today's webcast. And so if you would like to go there for a chance to win prizes, please go to that link that's in Zoom that takes you to the Anti-Siphon website where you can participate in a free CTF challenge based on today's webcast. We've been doing this for the last couple of weeks and we're getting better at it and better at it and better at it and better at it. And you're getting better at it and better at it and better at it. And so if you haven't done it yet, now's the time to try it. And with that, I think we're done. We have one webcast tomorrow, and then we're done for the rest of 2025. So if you've joined us in 2025, thank you so much for being here. If you participated in Hack It, thank you so much for coming back time and time again. We know that you could do anything with this time, and you chose today to learn about math and how computers talk to each other. And it's a little less, Doc, it's a little less make believe for me now. It's a little less make believe, but I still don't know how all this works, how electrons produced in some power plant somewhere travel across electrical cords and then into my. Hey, I'm doing the
You
best I can.
realize we only had 60 minutes, right?
I know. Doc, thank you for your time. Thank you for being with us today. And we'll pass on any questions that you didn't get a chance to get to, that maybe if you want to add it to your additional content or your workshop in the future. And I would love for all of you to take Doc's workshop in the future and his future training classes. Because, I mean, you got a chance to meet him today. You got a chance to see how he teaches. This is what you would get. And that's why we do these.
This
All
is
right,
it.
Doc. All right, Doc. Thank you. Megan, go ahead and kill it with fire, Megan.